The deadliest air-to-air missiles achieve kills without revealing themselves until seconds before impact. The target's radar warning receiver remains silent. Electronic warfare systems detect no threat. And by the time the missile's active radar activates in terminal phase, evasive maneuvers no longer matter. This is not theoretical capability. This is operational reality documented across multiple theaters. And it fundamentally changes what air superiority means. The conventional understanding of missile guidance follows a straightforward sequence. Aircraft radar locks onto target. Missile launches. Missile's onboard radar guides it to intercept. Target detects launch, deploys countermeasures, executes defensive maneuvers. The engagement becomes a contest between missile kinematics and target evasion. This model applied to semi-active radar missiles like the AIM-120 Sparrow, which required continuous radar illumination from the launching aircraft throughout flight. The launch platform remained committed to guiding the missile, vulnerable to counterattack, and unable to engage additional targets until the first intercept completed. The AIM-120 AMRAAM introduced active radar guidance, eliminating continuous illumination requirements. Once launched, the missile guides itself to intercept during terminal phase. This fire-and-forget capability freed launching aircraft to maneuver defensively, engage multiple targets, or disengage entirely. But even this description understates how modern networked engagement actually functions. Because the missile does not operate autonomously. It operates as a node within a distributed kill chain, where multiple platforms contribute guidance without the missile emitting detectable signals until the final seconds. The AIM-120D incorporates a two-way data link, enabling the missile to receive mid-course guidance updates from off-board sensors. This data link fundamentally changes engagement geometry and electronic warfare dynamics. After launch, the missile uses its inertial navigation system to fly toward a predicted intercept point based on pre-launch targeting data. This data originates from the launching aircraft's radar, but it can also originate from infrared search and track systems, from another fighter aircraft via data link, or from AWACS platforms, providing over-the-horizon targeting. During mid-course flight, the phase between launch and terminal intercept, the missile does not activate its own radar. It receives periodic updates via data link, allowing course corrections without emitting electromagnetic energy. These updates can originate from the launching aircraft if it maintains track, but critically, they can also originate from other platforms in the network. The AIM-120D's two-way data link allows engagements with the launching fighter's radar turned off. The missile receives targeting data from external sources, processes those updates through its navigation system, and adjusts trajectory accordingly. The launching platform remains electromagnetically silent. The missile remains passive, and the target has no indication an engagement is occurring until terminal phase begins. AWACS platforms, E3 Sentry or E7 Wedgetail, provide theater-wide surveillance and battle management. Their powerful rotating radars detect targets at ranges exceeding 250 miles and track hundreds of contacts simultaneously. AWACS can transmit targeting data to fighters via secure data links. Those fighters, in turn, can relay that data to missiles they have launched, enabling engagements against targets the launching aircraft never directly detected. This capability was demonstrated operationally when AWACS directed fighters to intercept targets beyond the range of airborne intercept radars. The launching aircraft fired missiles based entirely on targeting data provided by AWACS. The missiles flew mid-course profiles guided by external updates, and intercepts succeeded without the launching platforms ever activating their fire control radars. Fighter aircraft equipped with advanced sensor fusion, particularly fifth-generation platforms like the F-35, combine data from multiple onboard sensors and external sources into unified tracking solutions. The F-35's distributed aperture system provides 360-degree infrared coverage. Its AN/APG-81 AESA radar operates in low probability of intercept modes, and its data links receive targeting information from other F-35s, AWACS, naval platforms, and ground-based sensors. An F-35 can detect targets passively through infrared signature, receive corroborating track data from other platforms, and launch AIM-120D missiles without ever activating its own radar in search modes that would alert adversaries. The missile flies mid-course using network-provided updates, and the launching aircraft maintains low observability throughout the engagement. Naval platforms contribute through Aegis combat systems aboard cruisers and destroyers. Aegis SPY-1 and SPY-6 radars provide long-range surveillance across air and surface domains. These radars can detect and track aircraft at extended ranges, transmit targeting data through cooperative engagement capability networks, and enable fighters operating within those networks to launch missiles against targets detected by naval sensors. The missile itself remains passive through midcourse. Its active radar seeker, operating in K-band millimeter wave frequencies, activates only during terminal phase, typically within the final 10 to 20 seconds of flight. At that point, the missile has already closed to within its radar's effective range. The target's warning time compresses from minutes to seconds, and defensive options narrow dramatically. Reduced warning time degrades defensive effectiveness. Traditional beyond visual range engagements provided targets with extended warning periods. Radar warning receivers detected fire control radar emissions. Aircraft executed defensive maneuvers or deployed electronic countermeasures based on threat geometry. And pilots had time to assess threats and respond appropriately. Networked engagements compress that timeline. If the launching aircraft maintains electromagnetic silence and the missile flies mid-course passively, the target receives no warning until terminal phase. Radar warning receivers remain silent because no fire control radar is illuminating the target. Electronic support measures detect no missile seeker emissions because the seeker is not active. The first indication of threat occurs when the missile's active radar activates at close range, often too late for effective countermeasures. Passive targeting through infrared sensors or network-provided data eliminates electromagnetic signatures that trigger defensive systems. If an F-35 detects targets through DAS infrared sensors and launches missiles guided by AWACS updates, the target never sees radar emissions indicating they are being tracked and engaged. The engagement occurs without electromagnetic warnings that conventional defensive systems rely upon. Electronic warfare resistance improves when missiles receive targeting updates from multiple distributed sources. Jamming a single radar, whether aboard the launching aircraft or on the missile itself, does not break the kill chain. AWACS continues tracking. Other fighters provide corroborating data. Naval platforms contribute updates, and the missile receives guidance from whichever source maintains the most reliable track. This redundancy makes electronic warfare significantly more complex for defenders. Effective jamming requires simultaneous disruption of multiple platforms across different frequency bands and emission geometries. Achieving that level of coordinated jamming against networked forces exceeds the capability of most tactical electronic warfare systems. The defended target often does not know they are being engaged until missile terminal phase begins. At that point, kinematic options are limited. The missile is close, traveling at supersonic speeds, with remaining energy sufficient for aggressive terminal maneuvers. Defensive turns bleed aircraft energy. Chaff and flares have limited effectiveness against active radar seekers employing modern signal processing, and time available for countermeasures measures in seconds. Air superiority no longer derives from platform performance alone. The aircraft with superior speed, maneuverability, or weapons range does not automatically control airspace. Instead, air superiority derives from network architecture, the ability to integrate sensors across platforms, share targeting data through secure data links, and coordinate fires using distributed guidance. This changes procurement priorities and operational doctrine. Investing in individual aircraft capabilities without corresponding investment in network infrastructure and data link interoperability produces diminishing returns. An advanced fighter without secure data links to AWACS and other platforms operates at a disadvantage against less capable aircraft integrated into networked kill chains. Missile defense planning must account for engagements that provide minimal warning. Defensive systems optimized for long-range radar detection and extended reaction times become less effective against missiles guided by off-board sensors. Point defense systems, close-in weapons, and short-range interceptors gain importance as last-ditch protection when earlier detection fails. Coalition interoperability becomes critical. Networked warfare requires compatible data link standards, common identification, friend or foe protocols, and shared operational picture across allied forces. Nations operating advanced aircraft without network integration cannot fully exploit their capabilities, and adversaries can exploit seams in coalition networks where interoperability is incomplete. Future air combat will be decided by systems of systems integration rather than platform versus platform comparisons. The side with better sensor fusion, more robust data links, and more distributed guidance architecture will achieve kills before adversaries detect threats. This is not speculation about future capabilities. This is documented operational reality. The AIM-120 AMRAAM does not operate as an autonomous weapon. It functions as a terminal effector within a networked kill chain where AWACS, fighter aircraft, naval radars, and data links collectively provide guidance. The missile remains passive through midcourse, receives targeting updates from off-board sensors, and activates its own radar only in terminal phase when evasion becomes nearly impossible. This architecture reduces warning time, enables passive targeting, resists electronic warfare through redundancy, and compresses defensive reaction windows to seconds. Targets often do not know they are being engaged until interception is imminent, and by that point, kinematic and electromagnetic countermeasures face overwhelming disadvantages. Modern air superiority depends on network integration, not individual platform capability. The missile that does not use its own radar until the final seconds represents not a limitation, but a fundamental advantage. Because in networked warfare, the most lethal weapons are those adversaries never detect until impact is inevitable.